Hello. Okay, cool, that's recording. So today me and Zach, we're gonna be doing a physics video. I have no idea why you would think that we're qualified to do this, but you know, why not?
Yeah.
So, we're not saying that we are, like, savants or excellent at this. But yeah, so, Zach's gonna do the drawing, because he's good at drawing, and I'm not. I'm not sure if his artistic skills will be tested in this with Stickman, but it doesn't matter. Alright, so let's make a scenario for this. You are in a cage, and the only way to escape is you have to hit that dude with a rubber band because he is allergic to latex, and then he will fall over onto a plank of wood that's on a barrel. That'll catapult the keys to you. Okay, so now you want to go for a new window?
Yeah.
Good. Okay. So we're going to break this into a couple of parts. First part is just going to be, we want to shoot the dude with the rubber band. And he's walking in circles, okay? Oh no, he's pacing back and forth, so we want to find when to shoot him. The scenario makes no sense, I know. Basically, we're trying to predict where the rubber band will land. That's the first part. So first part of that in the, and I like this, as a first project. Whoops, sorry. Because it starts with extremely simple equations, and then it gets a bit harder, but it never gets that hard. So first we have a rubber band. Let's say it's 0.1 kilograms. So 100 grams. And then I looked this up somewhere. It moves 8 meters per second. Oh, wait, I just said that. Okay, yeah, so it moves at 8 meters per second. So 1 kilogram, 8 meters per second. So now, let's say we wanted to find the force of the rubber band. We would use the equation F equals ma. And I like to think of it as more of a concept than an equation, because that's what it is. I mean, he made up newtons, so, and it's basically force equals mass times acceleration. So basically, and it makes sense because the amount of force you need is how much the object weighs and how fast you want it to move, and that equals the force needed. And it's measured in newtons. Newtons are about 1/4 of a pound. Alright, so now we can calculate the force of it. So mass is 1 kilogram so can you write something? 0.1.
Wait, that's probably wrong.
Yeah, that's a bit big. 0.1 times times 8. So that would be 0.8 800 grams. So we know how much force it is. Now we want to find out where it'll go. So we have its acceleration. And then we want to find out how much will it lose due to drag. And then let's say it loses 0.5 meters per second due to drag. 0.5.
Oh, okay, 0.5 there.
And then can you draw half of an arc?
Half of an arc, like,
yeah,
like there?
Half of
half
that.
an arc, so like that?
Yeah, so once it gets to that point, this is why, so if you have something at a 45-degree angle, it'll move in an arc. And then there's its its loop. Its drag will slow it down when it's going up, but then it'll keep it moving. I mean, it'll slow its descent when it's coming back down. So, can you write on this side of the arc minus 0.5?
Right here?
Yep.
0.5.
M/S squared. And then draw another half of the arc, the opposite half. And then write plus. Cool. So then, we know that when it's going up, it'll lose 0.5 meters per second, but when it's coming down, it'll gain 0.5 meters per second. So when it's coming down, the air resistance is pushing it up, but when it's going up, the air resistance is pushing it down. So then, we want to find out how much energy is going each way. So if you have 180 degrees, which is just a straight line, it's going to be 100% of the energy going to the side. Do you want to draw that?
Oh yeah.
Cool.
So
100%. And then if you have something at 90 degrees, which is just straight up, 50% of it, 0% of it, sorry, 0% of it will be moving it to the side. So from that we can just assume that 45 degrees, halfway between 180 and 90, will be 50%. Because that's just logical. So now it's 4 meters per second to the side and 8 meters per second up.
okay. So what should I do now?
Right, draw something to the side and put 4 meters per second. Oh no, just
Just
there,
to- oh, there.
4 meters, and there, 4 M/S squared. I guess I should go into the reason that I'm not writing. I have something called dysgraphia. It's like dyslexia for handwriting. So basically my fine motor skills are bad. So my handwriting's bad. That's basically all it does. So yeah, my handwriting's bad, so I didn't want to do the drawing and writing for this. Because I wanted you guys to be able to read it. So I think that that's all for this tutorial, although I'll talk about what we're going to do in the next one. We're going to find out how far it's going to go. And then, yeah, we're going to find out how far it's going to go.
Okay. Cool.
Nice.
I don't know what they keep.
So once again, I don't think we're very qualified to do